um, um, our lectures in the first virtual CCE. This year, we had to switch the virtual mode, as was explained by Marcella a couple days ago. And the next speaker, for me, it's a pleasure and an honor to introduce Rashid Sunyaev. I think a lot of people already have heard of him in many different fields. He received he finished his diploma, his master's and undergrads in the Moscow Institute for Physics and Technology in Moscow, and his PhD from Moscow State University in '68. He's a professor at the Moscow Institute of Physics and Technology nowadays. He's also the head of the High Energy Astrophysics Department of the Russian Academy of Science, director of the Max Planck Institute in Garching, and he has numerous awards, including the Dirac Medal, Kyoto Prize, Craftwork Prize, Heinemann Prize, Alexander Friedman Prize, Bruno Rossi Prize, Gold Medal of the Royal Astronomical Society, Schwarzschild Medal, Bruce Medal, and Gruber Prize. And it's going to take too long to list all the prizes has received. Rashid has produced a significant, many contributions to various fields, from density perturbations in the early universe to the Cygnus X1 black holes and things like accretion disks. The one that I personally read the most and liked the most for personal reasons was a relatively short paper published in 1972 in a journal called Comments in Astrophysics and Space Physics, where I got the title back again. It's a very simple title: The Observations of Relic Radiations, a Test of the Nature of X-ray Radiation from the Clusters of Galaxies, where him and Zildovich basically laid down the foundations of what is now known as the Sunyaev-Zildovich effect, which is related to the difference in temperature of the microwave background radiation direction of clusters of galaxies. That at the time was a very interesting, clever idea, and nowadays is one of the cornerstones of observational cosmology, allowing us to determine parameters of clusters of galaxies and groups of galaxies currently at high redshifts and velocities and so on. So he works in many areas, a lot related to high energy astrophysics, of course, and he's the lead scientist of the Russian Spectrum Röntgen Gamma mission, where you have two famous telescopes, and eRosita and the ARTXC in different, the last one higher frequencies for X-rays, and it has been launched last year, has been a year working successfully, and it's going to be the most extended, most powerful X-ray survey in the next many years. So without further delay, I will pass the word to Rashid.
Yes, thank you very much. I can start, yes? I thank you very much for invitation. It's a pleasure. I never was in Brazil. This was dream from the childhood. There are beautiful verses in Russian, how beautiful is Brazil for children. And I remember this from childhood. And but it is a pleasure to be virtually in Brazil. Okay, I will speak today about our orbital observatory, SRG. And we are, how to say, yes, we now became very suspicious because everything is going till now well, and in space, you know, everything might occur any moment. Therefore, we are even afraid to say very loudly how good everything is going. But let us start. I will show you observatory itself. This is the Russian-made telescope ARTXC. We produced our own crazy coincidence X-ray mirrors in Russia, but comparing them with the Marshall Space Flight Center in United States mirrors, we discovered that American mirrors are still better. And finally, they flew to the space instead of Russian X-ray mirrors. It is 350 kilograms, and this is first grazing incidence telescope designed and made in Russia. This telescope, this huge telescope, is eRosita. It is 808 kilograms. You see 3.5 meter length and practically 2 meters. You see this dimension. But these are normal people. You see there are many of them from Lavochkin industry. And you see that spacecraft is significantly bigger. And this is a navigator platform with closed solar panels, which is in reality spacecraft, which is orienting us, dumping the data, memorizing the data on board, and doing a lot of different things. It is a pleasure to work with so well spacecraft also. Okay, let's go further. This is a Russian well-known launcher Proton, in reality Proton M modernized, but it has also here the fourth stage, which is the M3. This is a booster additional stage, which brought us to L2 point in the system Earth and Sun, directly to the distance 1.5 million kilometers from us. This launch was enormously beautiful, you know, smooth and nice. We were very, very happy and glad with it. This occurred on 13th of July last year, and we are very glad with this. Now we are practically one and a half year in space, and it's okay. I will tell a little more. This is our orbit. Very far here is the sun, our sun. It's our Earth. This is moon orbit. You see it. And this is the launch of our spacecraft. It went so. And this is L2 point. In L2 point, just when I am explaining this to children, obviously astronomers know much more. In this point, the centrifugal forces and gravitational forces toward Earth and Sun are balancing each other. And this distance is 1.5 million kilometers. This is our first attempt to fly to L2. Therefore, Russian industry was very careful, and we not went too close to L2, but it was rather, how to say, broad orbit. You see that this distance is practically the same as distance to the Earth. It's also more than 1 million kilometers. And we went, when we draw this, it was one of the last corrections. It was April this year, but now we have new corrections. We wish to decrease this orbit, its amplitude, because Russia is to north, and radio telescopes on the Russian territory twice a year see not well L2 point. They see the L2 point only for a few hours per day. And this is rather not good, because we cannot dump all the data. Now European Space Agency even is trying to help us sometimes, but people decided to decrease amplitude, and then all time the orbit will be visible, spacecraft will be visible from the ground. First 100 days of flight, this time, we used for adjustments, calibrations, and long, but today I will show you some of long observations of interesting areas and sources in the framework of performance verification. This was used for our flight. And now when we are here, in one half of the year, we are making whole circle around L2 point. And during this, I will show you next slide. What spacecraft is doing is 150 million kilometer Earth, and this is our spacecraft. And spacecraft is rotating, you see here, with period of the order of, not of the order, but exactly 4 hours per day, 4 hours. Therefore, every source on the sky during this scan is observed 6 times per day, but only once in a half a day, because our sun is moving to 1 degree for us, to 1 degree per day. Therefore, we follow the sun, and also direction of the main axis of our spacecraft is changing to 1 degree every day slowly. And therefore, in 1 day, we are getting this white strip, 1 degree white strip on the sky map. And you see here, this how it's going. And we return to the same source only after half a year. We can observe it again. But during 1 day, we are observing 6 times for 40 seconds approximately every source here. And this is a picture when there were not too many observations, but I should tell you that these big circles, they all intersect in the northern and southern ecliptic poles. You here, and here we have around this Russian, how to say, territory, and here around north ecliptic pole, we have the region of deep survey. You see here, immediately in this 1 degree, we saw cluster of galaxies at redshift 800s, and also the quasar, you see it, at redshift 2.7. It is just during the first 40 seconds of observation, we observed it here. Yes. In addition, our spacecraft is very good because it permits us not, when we are observing big regions on the sky, for example, up to 12 degrees, up to this is 150 square degrees. If we decide to scan them, spacecraft permits us to scan, and we are obtaining very smooth coverage. But XMM, for example, when it is observing, it's necessary just to make many points here, many pointings. But we are scanning, and this is very, very good images we are getting. And because orientation error is much less than 10 angular seconds, but much less. It's also the 1 angular second. And how to say this, and field of view of, for example, eRosita is 1 degree. Therefore, it's very good, we are keeping orientation. And angular velocity in this mode is 400ths of degree per second. This is Lavochkin industry, and I can tell you that all these numbers which are here, they are very, very conservative. They can do everything much better. I don't know, but I know only that, for example, Japanese space industry is doing the same. They are telling that their goal is this, but then are making order of magnitude better. All of you know about Lockman Hole. J. Lockman discovered this place on the sky when he was very young, and with 100-meter dish in Green Bank, he and several other people were observing the sky in 21 centimeter. And he discovered that this Lockman hole is the place where the, how to say, column density of hydrogen is the minimal on northern sky. In reality, it's close to minimum on the whole sky. And we chose this field and make here very deep observations. Observations of the order of 40 kilosecond per every point, equivalent to the pointing of 40 kilosecond, but we were scanning all this region. And what is the result? On 20 degrees, we discovered with eRosita 9,000 X-ray sources. These are not optical sources. All these sources are the X-ray sources. It's X-ray image. And among these 9,000 X-ray sources per 20 degrees, that's 450 sources per square degree. We have also 270 extended. 185 are already confirmed as clusters of galaxies, and we have spectroscopic redshift for 150 of them. There are many clusters of galaxies, even at very high redshifts. What we have, and we have several such fields which are investigated very deeply. But I already told you that we had in reality, when we started agreement with Germany, we were thinking how to divide the data, especially during the sky survey, whole sky survey. And there were different ideas all to work together, which is rather difficult because German community is significantly, German astrophysical community, X-ray community is maybe twice or 3 times bigger than Russian community. Therefore, it was also not good. Finally, 2 agencies came to agreement and scientists that we will divide the sky, and on one side there will be full priority, will be MPE, Germany, people who made the instrument. And another side will be given to Russia, to Space Research Institute in Moscow, just because country is supplying spacecraft, launch, and is responsible for every day of work with the spacecraft, at least for 6.5 years. This was the agreement. Why it is good? Because you immediately see how rapidly people are publishing the data, what results they are getting, in which problems they are most interested. This was the agreement. But I remember I was very interested in the history when I was very young. And I remember the story how the King of Spain and King of Portugal, they decided to divide the globe where Spanish crown will be, ruling, and where this will be, everything will be under the jurisdiction of the Portugal. Maybe you remember this, they divided. And Portugal was agreeing even to give part of Philippines to move this, this map more close to the to American continent. And finally they agreed, and Spaniards at that time didn't know that Brazil is going so far to the east, to the Atlantic Ocean, but Portuguese knew this already. This is the reason why all people in Brazil are speaking now Portuguese and not Spanish as a whole Latin America. It's rather interesting because you read this in the childhood, and now you see we are doing the same, but in space with the X-ray sky. Yes, may I ask you, Mr. Chairman, do you hear me? Everything is fine?
Everything is great, Rashid.
Okay, thank you. Yes, I will go further then. First instrument, I already mentioned it, this Russian instrument, Arctic Sea, astronomical, Röntgen, he was inventor of the X-rays, he discovered X-rays, astronomical Röntgen telescope, both in German and in Russian. We are telling not X-rays, but Röntgen rays. But for Brits, it is still unknown thing, X-rays, therefore they are telling X-rays, you know this. Arctic ray, and it is named after Mikhail Pavlinsky, this Misha Pavlinsky, person who was staying from the beginning behind this telescope, this was his idea to launch such telescope and his idea how to prepare it. It was designed in Kyiv and then Russian Federal Nuclear Center. We know this very well because my scientific father, Zeldovich, my mentor, he was working there for many years, and Sakharov, you know, also maybe name of Andrei Sakharov, well-known cosmologist, physicist, but also he was person who was working on the hydrogen bomb in this Russian Federal Nuclear Center. They, how to say, produced this telescope and made key tests. Energy range of this telescope is 5 to 30 keV. Field of view is huge, 34 arc minutes. This is very important to scan how, if field of view is bigger, we are scanning sky much rapidly and much more effective. On axis angular resolution is 1 degree, and energy resolution is 12% at 14 keV. There is excellent time resolution, 27 microseconds, much better than time resolution of eRosita. And I told already that crazy coincidence mirrors were produced in Marshall Space Flight Center in NASA. There are 7, I will show standard optical scheme for these mirrors. It's Vulture crazy coincidence mirrors, 7 mirrors, mirror modules, they're here, and here are detectors staying. You see this is collimator, each detector has collimator. This is the system. They have, every telescope has its own star trackers. Yes, this is where we are sensitive. It is on axis effective area of eRosita Arctic Sea. Arctic Sea is very interested because they were trying to make telescope comparable with NuSTAR, this American telescope produced in University in Caltech, University of Columbia, and in Jet Propulsion Lab. Everybody knows this NuSTAR and its characteristics, and these are characteristics of the effective area of Arctic Sea. And this is eRosita. But eRosita is sensitive only in very small energies, up to 2 keV. You see here. And then after 2 keV, this is just atomic physics. There is it's gold coded. There is a huge decrease of efficiency around 2 keV. You see this. But we are sensitive, we are working rather well, starting from 200 eV. From here, and our sensitivity is fine. It is comparable with sensitivity of eRosita around 4-5 keV of Arctic Sea. You see both instruments. At higher energies, Arctic Sea is much more effective, but at low energies, eRosita is really great instrument. Just to show you some observations of Arctic Sea. This is a result of Arctic Sea scanning of the sky of central region of our galaxy, the Sagittarius A star. You see here many different sources in vicinity of the center of the galaxy, but also there is diffuse gas which is reflecting X-rays. It's also observed here. And this image of new star, but new star with small field of view is making many pointings in the same region. And this mosaic of new star, which required 144 kiloseconds. Antarctic Sea is doing similar thing, rather similar, in 4.8 seconds. This shows how effective is these scans about which I told you. This is scanning of one pulsar. You see this is pulsar. And what is important, that there is wind, relativistic particles from this pulsar, shock wave, you see it here. It's Chandra. There are beautiful image of eRosita also, but people used in the beginning the old image of Chandra. You see there is a shock wave and tail and all these things, eRosita and seas, and also Arctic Sea seas also. Greenish, everything what is observed by Arctic Sea, and there is beautiful timing. Now I can show you the image, the sky map of SRG Arctic Sea. It's from 4 to 12 keV. Excuse me for Russian letters. I didn't recognize that it's Russian this morning. And you see many sources which we see in the galactic plane. This pulsar which I showed you is here. This coma cluster of galaxies which we observed also very long. And I have also beautiful image edition of the galactic center region. Scorpio X1 is too bright. And these are regions of deep surveys, which are connected with the north and southern polar polar regions, north ecliptic pole and southern ecliptic pole. And here is large Magellanic Cloud, many sources in vicinity. This is of the order Arctic Sea seas in the first survey of the order of 600 sources, which is very good result for half a year. Now, after 2 scans, they see more than 1,000 sources, and we think that there will be 10,000 source map, and this will be absolutely the best map in this band if we will survive 4 years in the same mode. Therefore, we are very happy. Unfortunately, our sensitivity of both instruments, of eRosita and of Arctic Sea, is lower than their predictions. It is because we are living in the epoch of solar minimum, and high energy particles are entering rather deeply solar system, coming to the vicinity of the Earth, and there is background, rather high background, which is practically 3 times higher than the estimates. No one X-ray spacecraft was in it too, but we measured, there is no protection by the magnetosphere, therefore we see rather high particle background. However, this background is extremely stable. And because it's very stable, we know background well, we can do it, we are becoming, now we know more, we are becoming, our sensitivity is increasing. Unfortunately, we are waiting now, if there will be solar maximum, then obviously the sun will be much more active, and there is a danger that particles of completely different type from accelerated by sun also will start to influence our detectors, and then background will be not stable at all. Therefore, this is also what we are discussing now. Yes, I hope that you all know about grazing incidence optics. And grazing incidence optics, it was a great surprise for people because normal mirrors do not work in the X-ray band because they do not reflect X-rays or reflect them, but at very shallow angles. Angles which is in the band of eRosita, it is up to from half a degree to 1 degree, this angle of scattering, you see, this angle. But in the case of Arctic Sea, it is much less. It's only several tenths or even several arc minutes. Therefore, this is why sensitivity of hard X-ray instruments is much lower than sensitivity of the soft X-ray instruments. In 1945, Walter in Germany, he was thinking how to create microscope in X-rays. But very rapidly, people recognize that if you have microscopes, then it's possible to produce telescope. And this is Walter type X-ray telescope. You need two surfaces. One surface is a hyperboloid, and second is paraboloid. You see them. It's just such rings, hyperboloid and paraboloid. And then after two scatterings, you are getting rather good image, which is not very far. You see this, normally it would be here, but due to two scatterings, it's coming too close and there is no coma. It's very good, and I took this. I have my own picture when I draw, but then I decided why I should do. It's much simpler to quote Wikipedia, because who is interested can look to this paper, Walter telescope and X-ray grazing incidence optics, and they will see all these beautiful pictures and many editions. What is the result? I showed you already 7 models of Arctic Sea, and these are 7 models of eRosita. You see them here. 7 mirror systems. Each model has 54 paraboloids and 54 hyperboloids inside. And there are 2 scatterings. There is also a magnetic deflector for particles. Yes, these are 7 huge CCD, X-ray CCDs created in Munich in semiconductor lab. And this is the biggest X-ray CCD which ever was flown. Now we have them in space. And they're working in space, and temperature is -84 Celsius, passive cooling, and it's very perfect and very stable temperature now. We are glad that from this point of view, everything is fine with detectors. And you see again how huge is this telescope. This is a person who I think is now taller than I am. Yes, now again, second region which I wanted to show you of deep pointing, scanning. And here we have the, again, of the order of 25 square degrees, this region. And you see what we can observe here. It's 20 degrees from galactic center. Galactic center is there. You see 18, 19, 20, 21, 22. And this is B, +1, -1, plane of our galaxy. And this region is obviously very, very rich. You see here a lot of X-ray sources. Pulsar, you see just this radio pulsar, it's not X-ray pulsar, but we see them easily. And a lot of supernova remnants. You see them here. These are all supernova remnants. And this is star-forming region. You see star-forming region, a lot of stars, and they're blinking every day. We see this also. You see them. This T Tauri star. This also is star. They're nearby. This star is nearby, but you can just see them. It's just projection. But you see the region. But for me, most interesting here are these red, green, and blue regions. I will tell you about meaning of the color, this RGB picture, but I can tell you this is the third component, important component of our interstellar matter. Everybody knows about molecular gas, H2, carbon monoxide, and everybody knows about neutral hydrogen, 21 centimeter line. But this is the gas which occupies, according at least to a Stryker and Chris McKee, which is occupying 80 or 90% of the interstellar space. Hot gas heated by shock waves from supernovae, decay of turbulence, and so on and so on. Hot gas everywhere around. There is a very good group in Portugal, which is working with Technical University of Berlin, which is investigating this theoretically, how it's heated and so on. We can measure this gas easily. I will show you next picture. You see here, we see the diffuse emission in X-rays. Blue and green colors correspond to high energies of photons. They are radiating by the gas with temperature close to millions and 10 million degrees. The red color corresponds to radiation of much colder gas with temperature of 100,000 Kelvin, up to 1 million. This RGB picture, you see it here. And in this picture again, even there is very strong X-ray absorption. We see 6,000 X-ray objects. Part of them are in reality very distant quasars, AGNs, which are far behind our galaxy. But there are many stars, a lot of white dwarfs, radio pulsars, supernova remnants. You see them. And also you see that supernova remnants are of different color. Why they are of different colors? Because this supernova is rather fresh, new, several tens of thousands years. Gas is still hot and it radiates with temperature is millions of Kelvin. And this is already elder, temperature is 100 of the envelope is 100,000 Kelvin, and therefore it has different color. We can do a lot of spectroscopy. I will show you, for example, well-known this image of this is now scan. It's only 200,000 seconds per point in half a year. This is the image of Cygnus loop. Cygnus loop is very, very bright supernova, huge. You see it here. And this is the spectrum of this region. And you see that we immediately see in 200 seconds, we see oxygen. This is second shell transitions in iron. You see many lines. Then there is neon, magnesium, you see silicon, and there is even sulfur. You see them. And this is 200 seconds. But if we are interested by supernova 87A in LMC, you remember this supernova, then we spend tens of kiloseconds using eRosita. And here is comparison of eRosita spectrum and XMM Newton, very long pointings also. You see lines of nitrogen, oxygen, neon, doublet, helium-like and hydrogen-like, this magnesium, silicon, sulfur again. But you see that our spectrometer is really working not worse than XMM spectrometer if we have rather long pointing. Yes, I will show you now I told you about half a year that we are able to make the map of the whole sky. And this is the map of the whole sky. And it is beautiful map. There are only 400 million X-ray photons. They are here on this picture. And I told you already that left side was produced by our group, and right side was produced by German group in Germany. For me, it was surprise because we were working, we are not permitted to look into the German data, and they are not permitted to look to our data. We both have them in archive, but we have no right we agreed not to look to this data except of calibration. And for me, it was surprise. When we got, half of this map, it was obvious that it is not good to publish only half of the map. And we decided to join efforts. And when we decided, I was present when two groups just coincided to hemispheres, to these two parts of this map. And immediately everything coincided, even significant part of software is different, and so on and so on. But it's okay, it showed that we are, we can believe each other that everybody is processing data very well. And what we see here, first we see the Milky Way. You see, this is the plane of our galaxy. It's very dark. Then I will explain you why it's so dark, but it's very dark. Then just above this plane, we see huge features here and also on the south. This is the North Polar Spur, which was observed both in radio and then in X-rays, just in the early days of radio astronomy and X-ray astronomy corresponded with this very bright feature. You see it. Here are Fermi bubbles also. But you can see also the brightest object on the sky, SCO-X1. We see it's huge dimension because its photons, it's so bright, and its photons are scattered on the interstellar dust, just as grazing incidence scattering, and therefore Scorpio X1 is comparable or bigger than Moon here, because due to this halo, due to the scattering on the interstellar dust. This well-known effect, but it's beautiful when you see it in many bright sources. This is the brightest object, but we were so happy. It is Cygnus loop, you see it, very bright supernova, spectrum of which obtained during 200 seconds. All this map, every point was observed, not every, because in the regions of the of the southern and northern ecliptic pole, exposure is bigger. But in reality, exposure is only 200, and majority of parts is only 200 seconds per half a year. Nevertheless, you see how bright are the well-known sources. And sources are, this is black hole candidate, everybody knows Cygnus X1, everybody knows Cygnus superbubble. Somewhere here is Cygnus A, well-known radio galaxy. Cygnus X2 is neutron star. Yes, I can show you CCE. This is the supernova remnant. This again supernova, very bright. This is Perseus cluster of galaxies. It's the third brightest X-ray cluster of galaxies in X-rays. There are another clusters of galaxies, Coma, which is beautiful, and Virgo cluster, in reality M87, it's here. Shapley supercluster, you all know this. This is the Centaurus cluster, Crab, Pulsar, everybody knows Crab. Orion Nebula, these are young stars. Vela supernova, Fornax cluster of galaxies, Large Magellanic Cloud, I already told about this. There is also LMC. It's a lot of different things. And there are many, many, look please to these blue sources here. These are bright galactic X-ray sources, accreting neutron stars and accreting black holes. You see many of them here. But each point here, this is also X-ray source. You see these small whitish dots. Altogether on this map, we discovered 1 million of X-ray sources. We see Milky Way, I told you, and traces of huge explosions in the center of our galaxy. It is a result of half a year when we were scanning the sky. I already told you about 400 millions of photons. This is also RGB map because you see photons from 300 electron volts to 600 electron volts. It's red color, they're soft. Green color corresponds 0.6 to 1 keV, and blue from 1 keV to 2.3 keV. And there are everything. There are blue sources, green sources, and a lot of red sources. It's cold gas, you see here. Relatively cold X-ray emitting gas. This is great. I will show you next. Yeah, and I should also tell you that there is million of X-ray sources. You see this, every dot is the X-ray source here. I think that to be real, we cannot just resolution of this picture doesn't permit us to show all million of X-ray sources, but when you're making it several, maybe 10 or 15 square meters with good resolution, then you see million points, it's easily, and it is beautiful. But you see how many of them are here. I am also very proud to tell you that we were trying to say what is the physics of these sources. And we know that 3/4 of a million objects on this map are distant quasars and galactic nuclei. And these are in reality supermassive black holes powered by accretion of matter residing in the centers of galaxies. This is 750 during half a year, which we detected the amount of black holes. They are far beyond the Milky Way on distances of hundreds of millions and billions of light years from us. But what is very interesting for us, we see also 20,000 extended objects. It is obviously supernova remnants, but mainly clusters and rich groups of galaxies with hot gas. In addition, there are more than 200,000 galactic stars with active coronae. I can tell you each of these stars has corona, which is maybe 1,000 or 10,000 times brighter than corona of our sun. They're flaring, we see a lot of variability, and I can tell you also that you will ask me how we are separating this, how we are able to separate these 200 stars. Very simply, we take the data from Gaia. All these stars are nearby, they are moving, they have parallax and so on. And then cross-correlating, you immediately finding what is the amount of this source. And QSOs, quasars, they are stable, they are not moving. Therefore, it is, but there are other reasons why we understand that these are quasars, but I will tell about this later. But nevertheless, it is, okay, I should try to be faster. Now I show you now several pictures from our hemisphere. Again, this Cygnus loop, but I asked especially Marat Kilfanov to prepare this and this picture. On this picture, you see the plane of our galaxy, this plane of our galaxy, and this plane of our galaxy is extremely dim. There is nothing, no radiation. What is the reason? Because we have a lot of gas, molecular gas, neutral hydrogen gas here, and this gas absorbs X-rays in this band very effectively. Therefore, our plane of galaxy is in absorption. But you see North Polar Spur, very bright, similar, even in the south, practically with similar dimension. But it is a little weaker than this, just due to the pressure is lower of gas. But there is also a lot of bright emission in this band, soft X-rays, and we are discussing, and all people are discussing, how much local bubble contributes, what is the contribution from heliosphere, place where solar wind is stopping due to interaction with local interstellar matter, or this is a gas in the halo of our galaxy. We are discussing these things. But when we move to harder X-rays, then you see that there is much less absorption, you see immediately, and then we can see a lot of point sources. They are practically absent on previous picture. You see a very small amount of bright source, of point sources, and here it's an enormous amount. And it's also very interesting how situation is changing. We are very glad to see these pictures. Now, there are a lot of discussions about exoplanets, and it's very easy to take all the nearby stars with known exoplanets, except of the Kepler spacecraft field, which is much deeper, and again cross-correlate this with our X-ray sources. And we immediately found 90 stars with known exoplanets, which are very active, which have active coronae and which radiates X-rays and give flares. They are variable. We took also all exoplanets in habitable zone, where, you know, in principle it's possible the life can survive because there is temperature is such that water there will be liquid and so on and so on. I can tell you that we do not see yet in X-rays no one star with exoplanets in habitable zone, which is good because for life it is good also not to have too strong level of radiation. I told you that we are observing only stars which are order or which are 3 orders or 4 orders of magnitude. The coronae are 1,000 or 10,000 times brighter than corona of our sun. Yes. Now I think that I still have time, yes, to speak. Mr. Chairman.
Yes, please. You do.
Okay. Now I will tell you a few words. We are excited by clusters of galaxies because when we are dreaming about this spacecraft, idea was that we will detect of the order of 100,000 clusters of galaxies, and we will find how they were evolving, how they are growing, so and so on, and that we were at that time dreaming about massive clusters of galaxies, and the total amount in the observable universe up to the horizon of our universe is only 100,000. And 100,000 clusters of galaxies, this was the goal, and we requested our German colleagues to produce such instrument. Answer was no, because we cannot produce, just impossible, device able to observe more than 1,000 or maybe 10,000 clusters of galaxies. But we told no to have baryonic acoustic oscillations. To keep these clusters of galaxies, we need 100,000. Finally, it was necessary to increase very strongly the dimensions of eRosita, and it is able now, thanks to Günther Hasinger and Peter Pradel, it's possible now to observe up to 100,000 clusters, all clusters of galaxies in observable universe, massive clusters of galaxies in observable universe. And we dream to do this. In the first half a year, we discovered already 20,000 of them. And we are certain that in 4 years, we will go to level of the 100,000 objects. This is typical cluster of galaxies, able 20 to 18. There is, as you know, thousands of galaxies are moving with velocity 1,000 kilometers per second, and this only few percent to the total mass of the cluster of galaxies, because main mass is in dark matter, 80%. And total mass is, we are speaking in reality about clusters of galaxies from 10 power 14 to 10 power 15 solar mass in dark matter. There is hot intercluster gas with temperatures from 10 to 100 million Kelvin, but extremely low density. You see 1 to 10 particles per 1,000 cubic centimeters. Therefore, it is very interesting. I wish to mention that practically in every, not in every, but in many, maybe in 20 or 30% of clusters, we see very good gravitational lenses. You see them here. It's a lot of gravitational lenses. And we dream that if we will discover 100,000 clusters of galaxies, then it will be additional many tens of thousands of gravitational lenses, what is very interesting. We pointed and we observed coma cluster of galaxies using Arctic-C, rather long, and it was detected in the band from 4 to 14 keV. We measured temperature and so on. And I will show you in the next picture, on the next slide, also the image of eRosita. This Planck spacecraft image, but this is negative diminution of the brightness of CMB in direction of coma cluster. And I can show you, this is image of eRosita. You see it. And this is a satellite. And we see it, we see the bridge here, you see between two, between galaxy and this satellite. We see the shock waves, we see cold France here. It's so beautiful. And we go, our dream is to go to investigate well what is occurring behind even R200. It's very important for us. But I can tell you also that this is the region 3 to 3 square degrees, which we were scanning for several, it's 70 kiloseconds we were scanning this region. And I can tell you this is not surprise, but it was beautiful to see here around, to discover many tens of distant clusters, which are at cosmological distances. Coma is very nearby. They do not have any relation to the coma, to this concentration of matter here, but our sensitivity is such that we see a lot of nearby groups and clusters of galaxies, but mainly these are objects at cosmological distance. distances. Also, this image is very similar to the Planck image, and difference is following that we have much better angular resolution than Planck. But when we are working together with comparing this data, results are beautiful. Just having brightness in our band and picture of Planck brightness, we immediately getting the distribution of temperature in every point here, because we are comparing, you know, this that effect. It provides us with pressure, and here we can derive pressure, and pressure depends on temperature. Yes, may I move further? Oh no, I will not discuss this. I can show you only that how we are trying to check and take into account the data on that effect. These are the regions. You see the division of the sky. There is Atacama Cosmology Telescope in Chile at 5-kilometer height. And this telescope in Chile observed on all these territories 4,200 clusters on 13,000 degrees. We discovered only 1,600 clusters are on our territory here. Majority are on German side. And what I can tell you that, but we discovered on our sky, on this whole sky, we discovered 8,300,000 clusters already, much more than Atacama Cosmology Telescope. And in the footprint of Atacama Cosmology Telescope observations, we discovered 4,200 clusters, and they have only 1,600. Surprise for us that we do not see all the clusters, and they do not see majority of our clusters. It is because physics is very different. They see the NE multiplied to T, and we are observing NE square multiplied to T in power 1/2. This is a difference, and I can show you this. Marat Gilfanov did this. What is the distribution of clusters which are coincide? This red, these are hundreds of clusters which just coincide in the eRosita and in the Atacama Cosmology Telescope clusters. We see them both due to a Z effect and due to X-rays. These green objects, they're very, excuse me, not, these are blue objects. They're very interested because we are observing them not, we are observing all these clusters, but not as extended by as point sources. And you see they are here also, there are many of them. They are produce much less photons, and photons are more concentrated to the center. And what is the most interesting here, that these are point sources. First idea was, let us check this with after the second scan of the sky. And immediately when we got of 60 or 70% of the second scan, we found that significant part of these clusters of galaxies occurred extended objects, and they are really clusters of galaxies. We just had too small amount of photons in 200 seconds. It's very interesting, and there is a lot of things which is possible to do together using this data from different spectral bands. It's very good and interesting. But there are predictions. You all know about South Pole Telescope, and this is data, present day data of the South Pole Telescope, and this is the sensitivity of eRosita. And this is a prediction what they will observe. This was planned for 4 years, 4 years gone. They still not here, but they're slowly moving in this direction. Here you see the mass. It is from 1 in power 10, in power 14, 10 times 10 power 14 solar masses in dark matter, and this 10 power 15 different clusters of galaxies, and this redshift 0.5, 1, 1.5, 2. And I can tell you that eRosita is absolutely strong at low redshift. Up to today, it is better than anybody else, up to 0.7 redshift. But above 0.7, it seems that a Z effect, which doesn't depend on redshift significantly, it's much better. And we see this, how to say, we have both competition and also place, how to collaborate, how to work together, and this is important. Yes, now I can tell you that we covered more than 50% of the sky now. We finish our second scan in December 12. Very soon we will have second full scan of the sky. And when we will get it, we can compare, and what we are doing today, we are observing every strip on the sky with the same strip, what sources it had half a year ago. And we discovered a lot of objects which became much, much brighter or which disappeared, tens of thousands. And it's very important, and it shows that our sky is enormously variable, and we see a lot of objects which are variable very, very strongly. For example, these are tidal disruption effects. We have many of candidates now. And you know all about tidal disruption events. This is when star, not very careful star, is moving around supermassive black hole, and where average density of black hole up to this distance is higher than average density inside star. Star is disrupted. Part of matter is going to infinity, and part is captured and creates accretion disk. And then, usual story, there is accretion and huge increase of variability to Eddington and even super Eddington, and then decrease because you are eating all this mass and then nothing to eat and you disappear. And you see the characteristic time is from 1 month to 1 year, and this 10 years. Therefore, it's important. And our characteristic, we are observing objects every half a year. Therefore, we are telling to people, look, this object became 10 times brighter. Let us look to it and look, let us see. And what is interesting that these are usually supermassive black holes with masses of sort of several million several million solar masses, which is like black hole in the center of our galaxy, and then it is eating star, and accretion rate is solar masses a year. When it is 1 solar mass a year, it's very, very bright. You know this. We are observing these objects, but I will show you now completely different thing. This is how we are proving that all the objects which we are observing are in reality supermassive black holes and quasars. Russia hasn't big telescopes. The biggest telescope is in Caucasus, this 5-meter telescope, but there is also, we have telescope of Kazan University in Turkey, 1.5-meter telescope. It is this, and this telescope is in Siberia, just on the boundary with Mongolia. Just few hundred meters, as I understand. All my colleagues were there, I never was there, but on the boundary of Mongolia, this telescope, and fortunately, when weather is bad in Turkey, it's excellent in Siberia and opposite. And I can tell you, we decided that we cannot observe, we have only a few Now we have also telescope of Moscow University, 2.5 meter. We cannot just observe more than hundreds of or thousands of quasars. It's impossible for us to make spectroscopy of millions. Therefore, we did the following. We took all quasars which we have, all these X-ray sources which we have. We took the data on photometry with them, and group of Alex Mishcherikov, a lot of his students and graduate students, they are using the machine learning and neural network programs. He develops SRG-Z, Spektr-RG Z machine, and it is looking among 500,000 X-ray sources discovered during first sky survey on our site. They are checking which of them maybe are quasars with redshift Z higher than 3. Then he is telling to our telescope, please look, and what they are observing. Look, this is quasar for at redshift 4, 5, 7, 6, redshift now 1.5 meter telescope in Turkey. You see here 4.237. Now they have also 2.8 QSO with 1.5 meter telescope. And this is 411 is in Siberia. Just recently, today, I will have editorial board. We accept paper about discovery of the QSO. Nobody knew about this object with redshift 5.4. And they all were discovered during 200-second observations of eRosita during the sky survey. And then small telescopes confirm this. It's very interesting, and I can tell you 90% success. The photometric redshift today, according to this neural network and machine learning programs, photometric data are producing redshift. They estimate is, for example, here it was 4.6.2. It is of the order of less than few percent. They can do this now. And it's very, very impressive because we are not afraid now to tell to people it is 90% warranty. People are getting really, they're discovering very distant quasars. It's very interesting how rich is this. I will tell you now story how we discovered quasar with redshift 6.18, but then we found that it's well-known quasar, but this is most extra luminous quasar among quasars at redshift Z.6. It's very impressive. I will show you. This is it. Its luminosity in the X-rays exceeds 3 times 10 to the power 46 ergs per second. It's very, very bright in X-rays, and the X-ray luminosity is comparable with its optical luminosity. It's already, paper is published in monthly notices, and it is an AstroPH, but all other quasars at redshift 6 or are not observed at all by XMM and Chandra, or observed, you see they are here. And we in 200, these are kiloseconds, tens kiloseconds of observations. And we just observe it, this quasar discovered it during 200 seconds, it's so bright. And it's not variable, we did not discover variability of this object. This Pavel Medvedev found it. Yes, we are very grateful to many people in the Lavochkin industry, which is working, this tens of people, many tens of people are working every day checking that spacecraft is doing well, that preparing commands, how to move to make our reorientations or what to do. And every day with us working 2 giant antennae of the Russian Deep Space Network in Bear Lakes, near Moscow, 64 meters, in Ussurisk, 70 meters. Ussurisk is at the boundary of Russia with North Korea and China. It's very far. It's very far. And I always myself thought that Ussurisk is, how to say, very north. It is more south than Rome, for example. It's very, very interesting that this is very good position of the dish. There is also a dish on the Baykonur launch site, which is also working with us practically every day, and many small dishes. I will show you why we are so interested in X-ray astronomy and what experience we had in this thing. First, it was Mirquant. There were devices from Russia, Germany, Netherlands, and UK on the Mir space station. In '87, we discovered very interesting hard X-rays from SN87A at that time. This is Granat spacecraft, also was cooperation with Germany, Granat spacecraft was with France and Denmark. It was beautiful observations of the distribution of positron annihilation line in our galaxy, and in addition, a lot of black holes, galactic black holes were found. For example, GRS 1915, everybody knows this very bright and well-known source. It just was discovered by watch instrument, Danish watch instrument on Granat. And we are working on integral. There was Russian launch, and we got for launch 25% share of observing time of this instrument. It was launched in 2002, and fortunately it continues to work. Yes, now about the story, how we came to this project, about which I told you a lot. In 1987 in Moscow, the country was celebrating 30th anniversary of the launch of first Sputnik. And it was permitted to have big international meeting in Moscow. A lot of space physicists and astrophysicists from different countries came to Russia, and it was told to us that if we will propose good physics, then maybe with international cooperation, it would be possible to organize several international observatories, orbital observatories. I was very lucky because Zeldovich, you know, my mentor, and this Andrei Sakharov, and this I at that time, and they agreed to, these people and 26 other well-known physicists agreed to support my project of to observe our galaxy and universe in X-rays. And good supporter of this was Rashid Sunyaev, plasma physicist, which was a key director at that time. And this was our project. And you see, it was huge, big, and a lot of, this was cooperation with UK, Denmark, Italy, USA, Germany, Switzerland, Israel, Turkey, with a lot of countries and a lot of devices. Unfortunately, this is our drama that, as you know, in the end of 90s and beginning of 2000, there were huge changes in Soviet Union. As a result, mission was delayed and canceled when many devices were ready to fly. I can tell you, for example, this device, JETIS, Joint European X-ray Telescope, is now under name XRT, is working on the Swift spacecraft. There are several other devices which are working on different American spacecrafts now. But at that time, this was just disaster for our group. It was very, very difficult for me to convince part of the group not to leave science. Time was very difficult in Russia, and I told that we will get mission. And in reality, I can tell you that there was a lot of negotiations. Finally, people told me country became smaller, please produce spacecraft should be smaller, rocket should be smaller, everything should be smaller. And we came with idea of this present day Spektr-RG, and starting of 2003, we started to work it. In 2008, there was agreement finally with Germany to do it. And, you know, in 2019, it was launched. But you can see how big part of the life of a lot of people in my group in Moscow, it was spent to see this successful mission, which we have now. I will show you additional things. This is on launch site. You see the Proton rocket, and this is a lot of young people, and some of people here are not so young, as you understand, but this is our SPECI team from my department. They're here, and this is the site. Rocket is huge and beautiful. Yes, I think that I should finish. There are many other things, but I am already too long. Many thanks for your interest, and if there are questions, I will be glad to answer them. Thank you.
Thank you, Rashid. That was a very, very interesting talk. Let's start with the questions. Let me see here. I see some hands up.
Yeah, Ricardo and Rodrigo.
Okay, so Ricardo.
Hi, Rashid, nice talk. I have a question, kind of technical. On the beginning, you were describing the solar minimum and how it affects the background. Can you talk more about it?
Oh, yes. Everybody, I can also, I hope that I can show you the background itself just for you, if I will find, because I thought that it's too detailed, but I will. Yes, this is, oh, it was, yes. This is the background, SRG eRosita per telescope. This is a contribution, what we see, some of AGN, galaxies, and mainly our radiation of our galaxy, Gala, and local bubble, and so on. It's just this radiation, diffuse radiation, gives us such spectrum. And this spectrum, this is 1 keV, 2 keV, 3 keV, 4 keV, and so on. And this is 200 electron volts. And you see it is bright and much brighter than detector background. Yes, but at energies higher than 1.5 keV, you see already particles are more important. They're coming through our detector and they're producing some energy release. Why it is high? When there is a solar minimum, then pressure of the solar wind and pressure of the magnetic field, which it is taking to the interstellar matter and to the cosmic rays, is very high. And cosmic rays cannot penetrate much deeper into the central part of the solar system. When this is during the maximum of the solar activity. But when solar activity is minimal, then this pressure of solar wind and magnetic field, which is frozen, is much smaller, and then these particles can enter much more deep. And we feel this as, how to say, as background, because particles go through detector and release some energy in it and on the boundary of it. And Planck had the same, even it is in completely different spectral band. And this is the reason why life is not simple, but because these are galactic cosmic rays, then this background is rather stable. But when sun will return, become much more bright, then they will be much more active. Then it will accelerate much more solar wind and much more particles, cosmic rays. All these things will push out galactic things further, but we will see a lot of particles and from the sun, which certainly will be time dependent. If there are coronal holes and so on, we will see much higher background, and there are many details which come. Then it will be maybe more difficult to work. Particle background will decrease very strongly. Maybe here it will be. It will give a lot of additional possibilities for us. But this background will be much more unstable. I thought in the beginning that this is something is maybe very specific for eRosita or Arctic Sea, but now Chinese published data from the very primitive particle detector, which is staying on the dark side of the moon. And they also detected very high background. Therefore, people know this, and it is normal.
Thanks a lot. That was a very clear explanation. Thanks.
Okay, Rodrigo Gonçalves.
Yeah, thank you. Thank you, Professor, for the amazing talk. It was very interesting to understand and to learn about that spatial version of the treat of Tordesilhas, splitting the sky into parts. My question is regarding to the galaxy clusters. I'm just wondering exactly in this plot, I'm just wondering if it's possible to use the gas mass fraction from galaxy clusters in order to constrain some cosmological parameters.
Or yes. Oh, yes. I can tell you that if this part, which I hadn't time to talk about, I will show you this. 1 second. No, excuse me, I cannot find 1 second. Oh, yeah. First, I can tell you about before clusters. We dream to find during, we have already 1 year of scanning, 2 scans of the whole sky. We finish second scan in December, but our plan is to have 8 independent maps of the whole sky and to observe everything during 4 years. 1 year we have, additional 3 years. After that, we will have pointings and we'll just observe most interesting objects. But one of the main ideas is to observe, to make, using 3 million of quasars, to make the baryonic acoustic constellations, to investigate. Because it's huge statistics, and we will do this. We plan to do this. Second, what I wanted to say you is the following, that we wish to do this also for the these clusters of galaxies. And these clusters of galaxies, it is extremely interesting because clusters of galaxies, I will show you, you know these pictures certainly, but where it is on, oh, I think that I will find now. Yeah, you know these beautiful pictures obtained by Volker Springel. No.
Já está enrolado aí?
Vamos ver se o Jorge pode ficar.
Yes, you know this picture, and this picture shows you the millennium simulation. Now there are many, much more new, and this is This dimension is of the order of 5 gigaparsec. You see it. And Volker produced at that time the slice which is 16 megaparsec thick. It's very, very narrow slice of the universe. Then you immediately see the cosmic web. You see here the distribution. And in every node of this web, there is a cluster of galaxies. And you know that clusters of galaxies have relatively very high, how to say, over density and so on. And it's possible to check with them how everything was growing, how everything is existing. This is the reason that today we are working and we are extremely interested in this curve. We need 100,000 of clusters to create it. You see here masses, 10 power 15 solar masses, 10 power 14, 10 power 13. And this is how many of these clusters are per cubic megaparsec. And this is result for redshift 0, redshift 0.5, and redshift 1.4. With 100,000 clusters of galaxies, we will get this situation and we will see how the clusters were appearing in the world, how they were growing, and how many there were at any point. It's a lot of very important, beautiful physics which you can study. And we dream to have this, to get this 100,000. Obviously, as that people on South Pole Telescope and Atacama Cosmology Telescope, they are also dreaming about this. But I think that within it is now, I don't think that it's in 3 years, but in few tenths, you are young, in few tenths of years, you will see much more than 100,000 clusters of galaxies, and you will see when these clusters started to go to kindergarten, to school, and what universe we have today, how it was growing. And this will be an enormous source of information. The same with black holes. We have now 1 million of black holes. We are interested to get 3 million. I think that we will get 5 million. And then with 5 millions of AGNs and quasars, we will be also studying the mass distribution at any redshift. And you see how easy it is with the brightest of these sources, how easy using only 1.5 meter telescope to get spectroscopy. And I know that your country is participating in JPAS. You will get a lot of information. Therefore, it is important just to understand how and what is possible, and then to discuss all these sides. Excuse me, I'm too long.
Thank you very much, Professor Sasiba. Thank you.
Okay. We have a few more questions from the observatory. Yes. Wendert. Wendert, you're mute.
Can you hear me now?
Yes.
Okay. Thank you, Professor, for your great talk. During the talk, you mentioned about BAO measurement, and that I think if I get right, you said that you wasn't able to get the BAO measurement. So could you elaborate more on that in BAO measurement, how they would compare with another kind of BAO measurement, as it would be X-ray selected sample?
Excuse me, could you please, or maybe the best is if Mr. Chairman will repeat for me the question.
Yeah.
It was with my computer.
Yeah,
okay.
The connection was not very clear, but when you're asking about the BAO measurements, you asked about the redshifts?
Yes. Oh, yes, we need redshifts, and we need to know practically for all clusters of galaxies, the precision of redshift, which will be few percent. And this is very important, and we are now with all this machine learning and so on, with new instruments which are going to come in different countries of the world. We think that there will be new surveys will provide us with huge amount of the spectroscopic or very good photometric redshifts, which will permit to do this. And we are giving immediately, we discovering our sources with precision few arc seconds on the sky. And this is very uniform, how to say, choice, because we are using them using the X-ray emission. And it's possible to analyze them very well and to find baryonic acoustic oscillations, both for quasars and for clusters of galaxies. I have no doubts that for quasars, for example, we will do BO at different redshifts for maybe 3 or 4 redshift bins. And it will be enormous information, show us how the when really the transition from radiation, from matter domination universe to the dark energy dominating universe really occurred, and how it was occurring, how smoothly. Everything will be visible on this BO if we will do this at several redshift bins. And statistics will be huge. I'm talking about 5 million objects, which is not too much for optics, but this is specially different, specially selected sample of the most interesting objects. I think that, is it answer to your question, or I should add something?
Yeah, that's answered my question. Yeah, thank you, Professor.
Okay, thanks. So one more question, Eduardo Rondon was in the list. Okay.
Yes, do you listen me?
Yes.
Okay, I have a question. Is possible to use the data of eRosita for objects in the solar system? For example, the comet or planetary atmosphere?
Yes, I can tell you, obviously, yes. And the situation is the following. For example, we observed one of the comets several months ago. People who are responsible for this, for data reduction and so on, they produced all information. I saw it. They just, because they are responsible also for calibration of the instrument, they do not have time to write paper. They're so busy. And I'm very unhappy. I told him, okay, let's do press conference and just tell to people that we observed comet and so on. There again, they wish to publish scientific paper and press releases after that. You know, this is just because we are in the first, now it's 1.5 years of the flight, but we wish to know device detectors, behavior of mirrors, behavior of spacecraft better and better and better, because then it is easier for us to get much more information about real physics. Therefore, and I cannot say to people, okay, you are responsible, you are not working. I know that they do not have time to sleep because they're really working at the, I told you about particle background. We are working with so many different things which are influencing the work of the spacecraft. I check it. I have friends who are working with Chandra, with XMF. Everybody has the same problem. They just have more people. You understand me? And in Russia, for example, we do not have enough people to work with everything. They're doing science, they're doing calibration, they're participating in some hardware for future things, and I cannot understand how they manage. But at that time, because they got this comet, they wish to publish themselves. But I can tell you, we observed comet. It is in X-rays, it was rather bright. It's interesting. We see different lines from it, and so on and so on. I can tell you even more, because there is some influence of the optics. It goes through our filters. We follow the motion of Mars, for example, and other bodies on the sky just due to the leakage of the optical radiation. But it's important not to cry immediately we detected them in X-rays. We should separate this leakage. You understand me? It's we should be. I was whole my life I was working in theory, and I can tell you, life of theoretical person is much easier because he has his problem and he is solving it. And here situation is such that you are responsible for many things which are unexpected. Okay, sorry. But yes, solar system is extremely interesting, but most interesting for us today is the boundary of the solar system with interstellar gas. We wish to detect shock waves there, places where particles are accelerated, and so on.
Okay.
Okay, thank you. So there's one more hand from the observatory, Paulo Alonso.
Yes, good morning and good afternoon to everybody. Professor Sunyaev, thank you so much for the lecture. Congratulations. We can see that important scientific goals shall be achieved in this project. I have two minor questions for you. When the Rosita project was idealized, what is the time period expected for this facility to operate in space? Okay, and I think that I can infer from the last question that all the scientific results produced from the project Rosita will be released to the astronomical community. I would like you to confirm this and to give us a brief idea about the time expected for the operation of the telescope. Thank you so much.
Yes, I can tell you first about operation. We have warranty time, how to say, warranty from our industry that we will work altogether 6.5 years. You understand me? 1.5 gone. Years gone. Therefore, we have in addition 5 years, which are promised to us. 3 years, we will continue to scan the sky because nobody did this. We wish to live. You know, spacecraft Rosat, people used Rosat data for 30 years. And we wish also make so that data of the SRG spacecraft all community will use for 20 or 30 years when, you know, this data. This is important for us, and we wish also to work after 3 years. The rest of 2 years, additional 2 years, we wish to work as, how to say, as observatory, observing different most interesting objects. I'm practically sure that if economic situation in Russia will be the same, nobody will, and we will continue work as well as now, nobody will switch off our spacecraft. We will continue. Question is in reality that, you know, many chips in electronics of the spacecraft and so on, they are not radiation hot enough and so on and so on. These things are important, and industry knows better when they give us warranty. Certainly they believe that it will be, our lifetime will be longer than 6.5 years, but how much longer, I don't know. Yes, now about the data, opening of the data. There is very strong pressure to German side from the European community that they should open their data, and they promise, at least they are discussing, to open part of their data already during next year, and result of the first scan somewhere in 22. With Russian, I told you, with Russian side, we do not have such pressure, but we feel ourselves, how to say, we feel the obligation that we should also open the data for whole world. At some moment after several years, I cannot say how many, but we plan to open our data. Germans plan to open earlier, with agreement that we will not use their part of the data until we will release a similar amount of our data. But it's okay. We agreed to this.
Thank you so much, Professor, and congratulations again. Thank you.
Thank you.
Okay. I guess I don't see any more hands. So let me ask you one thing, Rashid. Is there, you mentioned that for the full map, you did a cooperation with the German side. Are there different specific projects where the two sides are collaborating? And if there is it a process, proposal for something that can involve?
No,
both?
it is going a different way. We have the joint committee, and this joint committee discusses, and then proposal is for benefit of both countries. We understand that this is much better. Everybody is happy, you understand me. But at the same time, we understand that behind us, for example, in Russia, there is a big community which is just not so experienced, which wishes to work longer. And we have responsibility because for countries, this spacecraft and, you know, work with of huge dishes. This is, I showed you this 70-meter and 64-meter dishes, which are busy every day. It's very expensive, and we should understand this, and we should, you know, not to do, how to say, not to make so that country will not get return, scientific return from this data. But for me, for example, I am completely feel myself obligations that we should open our data at some moment, and they should be open for everybody. We ourselves, I told you, we are using data of Gaia, we are using data from Sloan, public data, which are open for everybody. And we are grateful to European Space Agency, to United States, to all countries who are opening their data. And therefore we should do the same. I have no doubts. Question is only that, unfortunately, if it would be 20 or 30 years ago, more than 30 years ago, I'm sure that Russian community was able to compete easily. Now situation is not so easy. Country became smaller, and there are many different realities. Therefore, it is not so easy. But we see this obligation. A lot of young people are working day and night. They understand that this is great opportunity for them to use this data, and time will come when we'll open this. I think this scale of few years, but Germany will open earlier. It's already obvious.
Okay. So are there any more questions for the attendees? I know we are a little bit late, but it was very. I'd like to thank you again, Rashid, for presenting this talk, and I hope that at some point after this whole situation, this whole virus situation is over, you can visit us personally.
Yes, I will be very glad. Thank you. Thank you for the invitation. Yes.
Bye-bye.
Bye. Bye-bye. Thank you very much.